Hi folks, in this video we're going to have a quick look at a calculation involving Young's double slit experiment. So an interference experiment using a double slit of separation 0.95 millimeters. Fringes are observed using a travelling microscope. The distance between the double slit and the fringes is 80 centimeters, and the distance between the centres of the first and the 21st dark fringe is 9.00 millimeters. Calculate the wavelength of the light used. So let's start off with the equation for Young's double slit, and then we will sketch out a diagram just to show what each of those terms represents. So in this experiment we would use a monochromatic coherent light source such as a laser. And that light will have a particular wavelength, and that's actually what we are trying to determine in this question. Now the light from the laser is already monochromatic and coherent, but if we're using a normal bulb then we would need to use a filter and a single slit to make it monochromatic and coherent. Sometimes it might be required to put a single slit in front of the laser if the beam is too narrow. So when the light from the laser reaches the slits and passes through the slits, then it starts to diffract as it passes through. And because we have two gaps, then we have two sources of light coming through, and they both interfere with each other, so that by the time that light reaches the screen on the other end, then we have an interference pattern, which means we have a series of bright fringes and dark fringes. So the distance between the double slit and the screen is what we call D. The distance between the slits we call A. And then finally we have the distance between the fringes, between the centre of one bright fringe and the next, or the centre of one dark fringe and the next, is what we would call Y. So that's fringe separation. So in the question we're told that the double slit has a separation of 0.95 millimeters. So we'll write that in 0.95 by 10 to the minus 3. We're told that the distance between the double slit and the fringes is 80 centimeters. So that's D, and if we convert that into meters, that's 0.80 meters. And we're also told that the distance between the centres of the first and the 21st dark fringe is 9 millimeters. So that means that we have 20 complete fringes in between the first and the 21st fringe. So Y is the separation of one fringe. So what we need to do is take that 9 by 10 to the minus 3, and we're going to divide that by 20. Which gives us an answer of 4.5 by 10 to the minus 4 meters. So if we look back to our original equation, to determine the wavelength, we'll see that we actually have all the values that we need. We have A, Y and D. So now it's just a matter of popping those values into the equation. So we have A, which is the slit separation, which was 0.95 by 10 to the minus 3, multiplied by Y, which is the fringe separation, which we had to calculate there as 4.5 by 10 to the minus 4, all divided by D, which is the distance between the double slit and the screen, which is 0.8. So if we put that into a calculator, we get an answer of 5.34 by 10 to the minus 7 meters. Or it'd be common practice to convert that into nanometers, which would be 534 nanometers. And just as a common sense checker, that does make sense because this is a visible pattern, which means the wavelength must be within the range of visible light, which is between 400 and 700 nanometers.